Okay, Assalamualaikum and salam sejahtera. My name is Muhammad Syed Amirul and my teammate is Nur Iskandar bin Mokhtar and Muhammad Fitri bin Nordin. Today I will talk about the assignment for the control system fundamental. Our title for this assignment is the hydraulic control system. For the introduction, hydraulic control system essentially is in a many engineering application because they provide the precise control over the fluid flow, pressure and the automation. These systems are frequently modeled as the second order system with the second order differential equation used to reflect their dynamic behavior. The dynamic response or hydraulic control system is often characterized by the second order differential equation when they're analyzing them. Naturally, frequencies, damping ratio, and the response time are all significant properties of the second order model.
Now let's move on to the application. Hydraulic system utilize fluid mechanics to transmit power or control force and motion, and their behavior can often be described by a second order differential equation. In a hydraulic system, a second order system can arise when considering the dynamic of fluid flow and pressure. For instance, let's consider a hydraulic cylinder which consists of a piston and a cylinder filled hydraulic fluid. The motion of the piston can be controlled by regulating the flow of the hydraulic fluid into and out of the cylinder. Next, where hydraulic control is used. Hydraulic systems have a wide application in industrial machinery such as presses, machine tool, plastic injection molding, metal forming machine, and hydraulic press. Hydraulic control is widely used. This system enables for exact control of force, speed, and location, resulting in efficient and accurate operation. Besides, hydraulic systems are commonly used in robotic and automation. Hydraulic systems are used in robotic and automation applications where precise and controlled movement are required. In robotic systems, pressure control permits precise positioning, force control, and coordinated motion. Now let's move on to the block diagram. This is a block diagram for the hydraulic control system, which is start with input signal and then controller CS, hydraulic system GS, output or actuator YS, and the sensor as a feedback. The transfer function of the hydraulic control system from the block diagram is TS equal to CS multiplied with GS divided by 1 plus CS multiplied with GS. For hydraulic control system transfer function, we put Kp equal to 1, gain K equal to 10, damping ratio zeta equal to 0.8, natural frequency we put omega n equal to 5 radian per second, S equal to 1. We put the value into this equation, 1 multiplied with 10 divided by S squared plus 2 multiplied with 0.8 multiplied with 5S plus 5 squared plus 1 multiplied with 10. Then we can simplify TS equal to 10 multiplied with S squared plus 8S plus 35.
For this, using the MATLAB, the block diagram that we get in the MATLAB, and this the command to get the graph. So this is the graph that we have show you in the simulation, the value that we get in this simulation. Discussion, the stability of the hydraulic control system refers to the ability to maintain a desired and a predictable response over time. A stable system ensures that the output remains within the acceptable limits and does not exhibit excessive oscillation or instability. To ensure stability, appropriate control strategies and design technique can be employed. In the conclusion, we can conclude that the hydraulic system applies fluid mechanic to the transmit power or control force and motion by regulating the flow of the hydraulic fluid. The position and the speed of the piston can be controlled in the such system.
Today I'm going to calculate the peak time, setting time, and percent overshoot. So the transfer for this model is 10 over S squared plus 8S plus 35. So the formula for peak time, which is TP, is pi over noted frequency squared 1 minus damping ratio squared. So just put the value here and we'll get TP is 1.04 second. For the settling time, TS, the formula is 4 over damping ratio times native frequency, and you can get TS is equal to 1 second. For the percent overshoot, the formula will be e to power of negative native frequency pi over 1 minus negative frequency squared times 100%, and we will get the percent overshoot which is 1.51%. The next question is to convert the system transfer function to the state space representation. So the transfer function is 10 over s squared plus 8s plus 35. So to get this equation, we need to multiply s squared plus 8s plus 35 into cx and 10 goes to cr to one side and another. So how do we get this? This is the representation for the derivative of which is number. So the c double dot represent s squared, c multiplies s. This one is derivative for 35. So equals to 10r, which is derivative for the r. So this question is the independent variable, which is all of these, and the dependent variable for this equation is c. So as you can see here, x1 equals to c. So we get x1 dot equals to c, which is this here. So it's equals to x2 and so on. So how do you get this one? It's just c3. So we just move all these numbers to the front of it. So how to get the state space representation? This is the equation. So x dot x2 dot x dot. So just get this number is 0, 1, 0, 0, 0, 1, and 35. X1, 8, x2, and so on. So therefore the 10 will be the r equation for the last part of this thing, and the state space representation is y equals to 1, 0, 0, x1, x2, and x3. Next, the question G is to calculate the steady state area for step input, ramp input, and parabolic input. So the first part is for step input. The unit step is Kp equals to S equal to 0, Gs, and Hs. So the Hs will be equal to 1, since we do S equal to 0, substitute all this and we get 10 over 0 is equal to infinity. So the Ss equals to 1 over 1 plus Kp equals to 1 over 1 plus infinity, which is 0. So for the ramp input, is Kv equals to lim S0 S times Gs times Hs. We get to this equation. Also, we substitute the S value equal to 0 and this equation, and we will get 0. So the S is equal 1 over Kv. So 1 over 0, and we will get infinity. For the last part, for the parabolic input, which is Ka is equal to lim this S squared Gs and Hs. So we will get this equation, and substitute the 0, we also get 0. So the Ss is equal to 1 over Ka equal to 1 over 0 and infinity. So the steady state area for this transfer function is 0, infinity, and infinity.
Control system involving a hydraulic system consists of the several key components. Together, these components form a closed-loop control system that use feedback to regulate and control the behavior of the hydraulic system according to the desired reference signal. So that's all. Thank you.